So let's get right started to our first session, where we're going to just link about how this this module links to this work called PAUSE, and also go back to sampling, introducing detection. So many of you might be familiar with the PAUSE initiative, but just if you aren't, just please be patient, and we'll remind you and highlight how it links with this module over the next 4 weeks. So PAUSE, in other words, is Population Assessment of the World's Snow Leopards. You'll see in bold the letters that make up the acronym of this program. And its main objective is to generate a truly robust estimate of how many snow leopards there are across the 12 countries in Asia, which is an area around 1 to 2 million square kilometers. And the task, I mean, it's a very challenging task, and it's through the GSLEP program and all range governments that are supporting this program. And it actually started and was launched in 2017 through the GSLEP Bishkek Declaration, with the ambitious goal of estimating the population by 2022. So how is it planned to go about this program? So to achieve this, the main objective of PAUSE, which is, PAUSE has many objectives, but going back to the main objective, which is arriving to reliable snow leopard population estimates, there's a two-stage process that has been identified by the technical panel, and it's set and has been set up by the GSLEP steering committee. So the first one, an important step, which links directly to this module, is developing distribution models for snow leopard. So the distribution maps we have today are really inadequate and require inclusion of require the inclusion of one of the most important factors, that of imperfect detection. And many of them do not include this parameter. And Kustub is going to share more about this later when we look at different maps that have been used in the past for species such as snow leopards and other species around the world. And then it's important to note that the second phase is related to estimating abundance, because distribution surveys do not give us information about abundance. So we have to do this in a second phase, which focuses on intensive sampling using camera trapping or genetic sampling. And this is what was covered in Module 1 of SLN's training initiative. So if this is what interests you, please go ahead and we can share the link to Module 1, and you can watch all of those videos related to that. But you may ask yourself, if we're interested in knowing how many snow leopards there are, which is abundance, why is phase 1 important? And how does it link to phase 2? So if you have any ideas, maybe please write it in the chat. It would be great to hear from you guys. Why do you think we need to first do phase 1? Whoop. And Kustub, you can add some ideas too. I'm interested to hear what everyone thinks. So phase 1 is the distribution survey. Ranjana says to extrapolate density. Great. And are there additional meanings? Okay, to build a baseline to measure the impacts of conservation effort on the species. Yeah, Nilufar, this is actually a wider goal for PAUSE. So yeah, you're not far off. Ranjini is writing to get to know where the concrete efforts for phase 2. Okay, so help plan for where to go and do surveys. Great. Kustu said he just loves to do surveys and might as well add an extra task to PAUSE. Why not? Give us a little headache. Rab says information is king. I agree with you, Rab. Okay, let's collect as much information as we want. These are all valid responses, but I think one of the main reasons to have phase 1 is it helps us reduce potential biases in our national, regional, and global estimates. So some of you might be familiar with this publication by Surya Wanshi et al. 2019. And it suggests that if we only sample high density areas only and use this data to extrapolate for regional or global estimates, one is likely to make biased projections. So you can see here, if the study area is very small, the estimate on density tends to be much larger versus larger dense study areas for snow leopard camera trapping. The density tends to be estimated as much smaller. So this publication underscores the problem of reporting uncharacteristically high densities for studies that are mainly focused in small areas. And this is most likely a function of selecting the best habitats. So there are some issues if we were to extrapolate these best habitats on the map here to all the predicted IUCN distribution map, as Ranjana highlighted. And it might overestimate the snow leopard range because we've only been surveying in these high areas. That's one reason. So that could be a potential bias that might come into our estimate. So it's important to understand, okay, where are they distributed? Another example that many of you might have heard about is the bias in Mongolia, and they've actually shown it. And you can see in this map, the black areas, all the areas that they have covered camera trapping. So they have very intense camera trapping surveys in these black areas. And underlying this map is actually the occupancy map of predicted where snow leopards do occur. And they assess the coverage of where their cameras are currently covering in terms of occupancy. And you will see that from this map, I'll just show you with this arrow, they are currently actually overestimating the population in Mongolia by around 23% because these areas are covering the high occupancy areas, which is the darker areas in the map. And as you can see, they hardly have any camera trap sites in these lower occupancy sites, which leads to potential bias. So the teams in Mongolia are now planning actually to cover the less suitable occupancy areas, and they've actually just completed this in order to reduce this bias. And Ian will share more about this process and tools to do this in session 4. But in summary, the distribution map allows for a kind of stratification in order to reduce bias in the selection of sites for this phase 2. So that's one of the reasons we also do it. We also do it because we love collecting data, and that is completely fair. So let's now zoom in and look at what parameters we need for estimating the pause process. So if you remember from module 1, the first is abundance, total number, which is part of phase 2. And if surveys are completed multiple times, we can also get rates of survival, reproduction, and movement could be possible parameters we could estimate. But you may remember this image of the number of ibex in our potential study area. So if this was our study area, these were the number of ibex. How many animals are in this area? We could actually count them if we saw all of them, and we could say, okay, there are 20 animals. So the total abundance would be 20. For phase 1, and we would be assessing the area in terms of population distribution. One important parameter that we could use is proportion of area occupied. There are different parameters used depending on what model you use, your different approach, your aims, but one parameter could be proportion of area occupied. And if surveys are completed over time, the probability of extinction and colonization could also be estimated. So for going back to our example of ibex, we could, for example, lay grid cells over our study area. And these are here, they're 20 grid cells. And you'll see the darker grid cells are the one that the ibex is present. So then you could estimate, okay, so what proportion of my study area has ibex? And it could be 10, in this case it's 10 out of 20, and that's 50% of the study area is ibex. And that's a way to actually calculate your distribution of your population in this case. And you could, there are different spatial scales you could do this. You could do this at the smaller spatial scales, the scale, and this is the same variable, but a bit different. In this case, we have 60 grid cells, and ibex are present for 20 of them. So in this case, they are present in 33% of the study area, is an example of the case. But with both of these, abundance and area of coverage, we have to go back to how good is my estimate? And many of you maybe remember this from module 1. And we really would like to encourage everyone to think, whatever model you're using, back to the principles of, is it accurate and is it precise? And we're not going to go into much detail about this today, but we sent around that email and we'd encourage you to watch that if you're unsure about these principles, to remind yourself, because I think we will be touching upon this over the next four sessions. So we discussed in module 1 that there are common sources of error for our estimate, and these include sampling and detection error, and these will influence accuracy and precision of our estimate. There's also sample size that may influence the precision of our estimate, with small sample sizes increasing variance, for example. But do people remember, does everyone remember how we can report these errors? Because it's nice to know, okay, that these errors exist, but how do we report these errors when we're calculating our estimate? You can write it in the chat. So the question was, how do we report errors that might be linked? Sampling errors, detection errors. Because it's nice to know, okay, yeah, that these are sources of common errors that can happen when calculating our estimates of abundance or area of coverage, but we can actually report what these errors might be. Okay, I see some are coming in. Standard error and confidence interval, yes, that's one of the ways that we covered last time. Thank you, Ranjana. Calculating standard error. Thank you, Rob. Mean and standard error. Yeah, we can link to mean, which would be our estimate, for example, standard error. Okay, great. So we covered a range of these. Also, 95% confidence intervals can be used, standard errors, variances. There are different ways you can look at this. And one of them is also calculating the parameter of detection. So let's look and focus on this detection parameter. So what if there's an example, a situation where there's vegetation in our study area. So this vegetation limits our ability to detect all of the animals of interest. So it limits our ability to detect all of the ibex in this case. How would this influence our estimate? Would it bias our estimate? So we can look closely here. So the red grids here are areas we would survey. So we can pretend that our study area is hundreds and thousands or thousands of kilometers squared, and we can't cover the whole area. So we're going to sample, right? And if we sample, we cover only a proportion of our study area. And sampling means it's an estimate. It's not the true full population. It's potential mean of how many individuals are in our study area. But in some cases, there's vegetation. So when we come and sample, we might not actually see all the individuals that are actually there. So this is an example of, if you imagine each of these grids, these red grids, had a letter, A, B, C. And we actually knew how many animals were in each of the grids. And Kustub has so nicely prepared this for us already. And this is the real world, how many animals are actually in each of these red grids. But when we went out and did our survey, these are how many we counted. And you can see it's much less. In this case, when there were 4 individuals in this grid, for example, A, we actually only counted 2 individuals, and so on. So as you can see, then when we're counting the mean, okay, now we want to estimate how many individuals are in each grid cell, which allows us we do this by calculating the mean. In this case, in the real world, there are 3.3 individuals per small grid. But our estimate suggests 2.5 individuals per small grid. And we can calculate the standard deviation to look at this error of how wide it varies. But you can see that because we can't detect all the species, our estimate is actually off. It's actually biased. So without accounting for detection, we can bias our estimate. And then I'm just bringing you back to this. This might help you visualize what we mean by bias. If our real estimate is here, but we're calculating from our sample an estimate around here. So in this case, for example, if we were calculating density, which is the number of animals in a given area, which is number of animals in a given area, we've actually counted the count of number of animals we've counted over a given area. And due to the grass, we didn't see all the animals that were really there. So our parameter C risks being negatively biased. So counts represent some unknown fraction of the animals detected in our sampled area. So it's an unknown fraction, and we want to try to estimate, okay, what is this fraction in order to get our true estimate of density? And that's when the detection probability parameter comes into play. And what we need to do is fix that bias in order to introduce this new parameter that we call the probability detection that we can put here next to area. And this will help us estimate the true density while accounting for detection. So as you remember from module 1, this detection probability is this kind of like this devil that we need to address all the time, not only in populations distribution surveys, but also population abundance when we do camera trapping with spatial capture recapture, for example. We also in those models try to account for this detection probability. So in the next 4 sessions, we're gonna be talking the whole time about this nuance factor and trying to relate it, though, however, to distribution surveys. So highlighting how proper inferences really require information on this detection probability, especially for elusive species such as snow leopards, which you're unlikely to always observe while going out and doing your survey. So just the last few things to highlight, and then I'm going to pass it over to Kustub. What factors might influence detectability? And we're going to go over this a lot over the next 4 sessions, but just to give you a taste of what factors might include detectability are things like the species biology. A snow leopard is so well camouflaged in its environment. If it's so well camouflaged and we don't see it all the time, that's going to actually decrease its detectability. And we might need to, the detection parameter might actually be very low. And our estimate, therefore, might be really biased. And there are other factors that might influence, like climate, the time of day we do our survey. If we're doing our surveys of snow leopards at midday every day, that might influence whether we see them or not, because they're more active during the morning or the evening. How our observer efficiency, whether it's me going out or whether it's Kustub going out, there might be a very, very different detective probability on whether the animals are seen. So all these factors influence whether the species is detected. And it's important to highlight that it's hard to look at relative abundance, for example, without an understanding of detection. So without considering detection, we would be assuming there's a constant detection probability between one area and another area. And this is rarely the case. And it's rarely the case for cryptic species, such as the snow leopard. So we always have to correct and deal with detection. And there are many ways to deal with detection, and that's what we'll be trying to discover over the next 4 sessions. And one way is, for example, by standardizing the way you plan your surveys, the way you sample. You can try to control for such variations. And for example, always doing your surveys at the same time. So there's not this difference in the time when you go out your survey that might influence detection. Another way is to use covariates. And this can allow you to account for variation sources and control for this kind of variation. However, one must know, and I think this is something Daryl actually highlighted and mentioned to us, it's not always good to use covariates that affect the presence of the animal and also the detection of the animal, because you won't be able to maybe distinguish whether this covariate is influencing detection or it's influencing the presence of the animal itself. And if you don't know if it is influencing those two, it can bias your final estimate on distribution. And this is especially important for models such as presence-only models, such as Maxent, because you don't actually distinguish these two parameters. While occupancy, as you'll learn, we'll discuss later, we actually distinguish these two parameters to try and address this. And Kustu will be sharing more about these different ways, these different survey techniques. So finally, in summary, not correcting for detectability can result in biased estimate. And that's all I would like. If anything, you walk away from today's presentation, that's all maybe just keep in your mind. It can result in biased estimate, and it's just something to think about and think, okay, how good is my estimate when I come home from my survey or from my population assessment? Because as many of you know, all models are wrong, but some are useful. And the principles of sampling, stratification, modeling, errors that we discussed in module 1 will remain the same in this module. So we really encourage you to watch module 1 videos if this is unfamiliar, if you're unfamiliar with it. And remember that it's important to have good data and good designs from the start, because models can only correct a little bit later. So yeah, so I think now I'm going to pass it over to Kustu. But if anyone has any questions before we move on to Kustu's presentation, please write it in the chat. You're on mute, Kustu.
Yes. Okay. Can you hear me? All right. So there's a question by Luciano, and I'm just wondering maybe we should take it a little later, like ideally in the next session when we discuss covariates and their applications a little more in greater detail. But if you'd like to still respond, I think that could be good too. So I think he's asking, so you suggest to check the covariates for each of the parameters, keeping the other in turn one.
Yeah, I mean, that's when we're comparing models and things. Yeah, I think let's address it in the next session, because it will influence also the way in our discussions on making models for occupancy, Luciano, because it's the same principles, I think, for Maxent and for occupancy. So it's worth addressing in the next session.